Hello all. Welcome to section 3.4, a nice large section in your book that covers the qualitative prediction of acid strength and the comparison of acidities using what's called the ARIO method. This is a method that your book purports as a very good, or it puts forth as a very good way to, in general, determine the which of two or more atoms or protons can be more acidic in a molecule or in a range of molecules. It's not a perfect system, but we'll go over some of the limitations, and we'll also talk a little bit about how best to use this or when you probably shouldn't use it. So, to start off, ARIO is a little acronym that stands for atom, resonance, induction, orbital. And we'll get into what that means here in just a second. So, as a general thing to consider, let's look at this reaction. So we have some acid plus a base goes to A minus plus BH plus. Okay, and we know that this reaction occurs by the base using one of its lone pairs to, to take a proton from the acid. And the electrons between the H and A come right back onto the acid to get our A minus. All right, so this is the reaction that we are considering, but this is all very general. What if we instead move into the real world and now we're looking at a reaction like this? So we have some nitrogen with a hydrogen plus some oxygen with a hydrogen, and we are trying to determine what will happen in this reaction. How do we do that? Oops. Well, it's kind of hard to say because at the moment we don't know which of these molecules is the most acidic, do we? We know that both have a proton that could be taken and both have a lone pair that could act as a base. So what we need is a way to determine or qualitatively compare which of these might be the most acidic. And that's where ARIO comes in, because we will compare the conjugate bases of these molecules. So we'll leave the nitrogen, we'll do that one in orange, and um, we'll leave the oxygen-based one in blue. Okay. So looking at the nitrogen, first rule that we do every time when we're looking at a qualitative assessment, like using ARIO, is we have to draw the conjugate base of our molecule in question. So first we draw the conjugate base. There we are. That's the conjugate base. I'll put CB down here for conjugate base. Okay, and for the oxygen one, we have there we are. That's the conjugate base of the oxygen molecule. Okay, so now that we have the conjugate base, we can start to apply the ARIO rules. So first, let's look at A. A stands for atom, as we said. So here in the atom category, we are assessing the electronegativity of the atom that has the negative charge that results from the proton leaving. So in both conjugate bases, we're looking at the atom with the negative charge. The reason why we're doing this is because since there's a negative charge that occurs due to the donation of a proton, the atom that is the most electronegative will be the most stable because the most electronegative atoms can stabilize the most charge. So in this case, you can either look at section 1.3, I believe it is in your book. Let's see, section 1.3, which tells you about electronegativity. Oh no, sorry, it's 1. Yeah, is that right? 1.3? I'm having a look now. 1.5, sorry. Table 1.1 in section 1.5 can tell you about electronegativity, or you can remember the general rules of electronegativity in the periodic table, which states that it increases as you go right and up the table. But for now, what we can do is we can have a look in your book at that table, and we can see that between nitrogen and oxygen, which are the atoms that had a negative charge in our structures, between those two atoms, it looks like oxygen is the most electronegative. So switching back over to look at our structures again, if oxygen is the most electronegative, that means the conjugate base is the most stable. And if the most stable conjugate base means that you have the strongest acid present. So since you have the most stable conjugate base, that means it will be its acid will be the molecule that gives up its proton, and the other will act as the base. So this means that our reaction now, we've determined from the Ario rules, will have this structure, where the products we form are this positively charged it's called an amine or an ammonium with a positive charge, this positively charged nitrogen group, and the negatively charged alkoxide. Because normally this is an alcohol functional group, and now it's called an alkoxide when it's negatively charged. And we know this happens by the nitrogen's lone pairs taking the proton and the electrons coming back to the oxygen. Okay, great. So that's A for atom. But what about if we have two molecules like this? Okay. Here, these two molecules, they are only different. Actually, let's do this. Oops, sorry. Let's make them both sulfurs for fun. There we go. These two molecules now, they both have the same atom. So how do we determine whether which one of these might be the most acidic whenever we try to react them together in an acid-base reaction? So just like before, the first thing we do is determine the conjugate base for both. And in this disulfur molecule, the conjugate base looks like this. And in the this this mercaptanol, this mercaptan here, or it's called a mercaptoethanol molecule. That's the conjugate base. Okay, so if we try to use atom again in ARIO, we will quickly find, so ARIO, if we try to use atom here, we'll find that, in fact, both are the same, right? We just talked about that. So let's look instead at R, which is resonance. And what resonance says is that if you can take the negative charge that's generated in the conjugate base and you can distribute that negative charge throughout the molecule in some way, then the conjugate base will be more stable than if there was no if there was no resonance structure at all. So can we make a resonance structure with the orange one? I don't think so, because there's no double bond near the negatively charged sulfur. However, in the blue one, we can, right? Because in the blue one, we have this type of structure that could be possible. Let's give ourselves a little more room here. There we are. And so now 2 atoms can share the negative charge instead of just the 1. So this is actually the most stable conjugate base by the R of ARIO. And so your conjugate, or your reaction then looks like this, because the molecule in blue is the strongest acid. And we know it's the strongest acid because its conjugate base is the most stable. Whoops. There we are. And we know this reaction occurs by the lone pair on this sulfur coming and taking this proton, and those electrons coming right back to the other sulfur there. All right, so that is the R in ARIO. Okay, so that is the A and the R. Next, we're going to look at the I. And to look at I, we're going to kind of think about a similar problem that we just had. So here, let's look at these 2 molecules. Okay, here's one. Actually, let's not use those molecules. Let's use these 2. Oops, there we are. Great, here's one, and here's the other. Draw that a little bigger. There we are. All right, so when we react these 2 molecules together, what will be the acid and what will be the base? I want to make sure I can actually see this. I think this F might be a little difficult to tell. There we go. So hopefully you can see now that is a fluorine. Okay. As we said before, we're looking at ARIO, right? So here, notice that the atoms are both the same, so we can't use that. Neither of them have a resonance structure that can be made, so we can't use that. Now, I guess we're left with the I, which stands for induction. That's right. Okay, so again, the first step here is to find the conjugate base of both. So here the conjugate base of this alcohol would be this alkoxide. And the conjugate base of this alcohol would be this alkoxide. All right. So what the I of the ARIO stands for is induction. And what it says is that if you have a polar group, like say for instance, let's have, for a little example, we'll use this molecule, very, very simple molecule. If you have this molecule, this methanol, this methoxide, the negative charge here is not stabilized by anything, right? But the rule of induction says if you instead have some atom that is electronegative near the alkoxide or near the negative charge of the conjugate base, then the resulting polar character of the carbon heteroatom bond here will result in a net partial positive on the carbon and partial minus on the chloride. Now, when that happens, the partial positive on the chloride is actually going to stabilize the fully negative charge on the oxygen. And there will be a larger dipole moment that happens going the other way. And so since you have this stabilizing partial positive charge here, you will in fact get a more stable conjugate base, which means of these two, the acid will end up being, or the acid in this reaction will be the one that has induction, the orange one. There we are. And the base will be the one without any induction. This has been I from induction, or from the ARIO. Okay, so then in last of ARIO, we're almost done here, we have the O. So to look at O, let's look at a very simple example of these two molecules. So in these two molecules, oh, this one should be blue, right? If we were to put them together and determine which one would be the acid and which one would be the base, we could use the same ARIO techniques to determine which of their conjugate bases could be the most stable. So here, we only have carbons in the structure, so it seems like A can't be used. We're actually going to look at, let's see, these specific protons here. There we are. And R cannot be used because this proton on the double bond is not actually in a p orbital, it's in an sp2 orbital, and so cannot participate in any resonance in the molecule. I'll leave that to you to confirm that, but it is that is the case. I cannot also be used because they don't have any electronegative atoms, causing a partial positive charge that stabilizes the conjugate base. But you know what? We didn't even make the conjugate bases, so we should do that before we move on. Conjugate base of this one is this negatively charged carbon anion, sometimes called a carbanion. And this one, its carbanion conjugate base looks like this. Okay, so what we're going to talk about now is the difference between these two using the O, which stands for orbital. Okay, so the orbital rule basically says that if you have an sp2 hybridized anion, it is more stable than an sp3 hybridized anion. And an sp hybridized anion is more stable than both of them. So in terms of stability, sp more stable than sp2, which is more stable than sp3. And the reason why all boils down to how far away these charges are from the nucleus. So if you have a nucleus here, we'll just symbolize it by this dot. An sp3 orbital looks like this, right? Where the charge can be all the way out here if it wants to, really far away. I mean, it could also be close, but it could be that far away. And the reason why is because the sp3 orbital is made up of 3 p orbitals and 1 s. So it has mostly p character with a lot of electron density very far away from the nucleus. The sp2 orbital, however, looks a little different. I'll draw a little arrow here so that we can know what we're talking about. sp2 orbital looks a little closer to, it can't go quite as far from the nucleus, and the reason why is because there are only 2 p orbitals and an s orbital that is mixed together. So that means this orbital will have a little more s character and will sit a little closer to the nucleus, and so if you do have a negative charge, it can't get quite as far away. And the reason why it can't get quite as far away is because it has slight s character there, or more s character than the sp3 orbital. Oh, yeah, these should say, we should be talking about, oh, sorry about that. There we go. This one should be over here. There we are. Okay. Sorry for that. That might have been, sorry if that was confusing. When I realized what I did, it was confusing for me too. Okay. So like I said, sp3 orbital on the right, it has a chance to be the least stable because the negative charge can be the farthest away. sp2 orbital, negative charge can be a little far away, but closer to the nucleus. And an sp orbital, if the nucleus is here, is much closer to the nucleus. And that is because whenever you mix, what you're mixing together is an s and a p orbital. And so that has a 50-50 mix of s and p. So that's why the lower hybridized orbitals contain a negative charge easier. And so here, the conjugate base that we would expect to make is this carbon ion there, and that would be the most stable. So that would be the most acidic there. This is kind of a weird example because, of course, carbon cannot have 5 bonds. In a magical world where it could, you could make a positively charged carbon that way, but we'll just leave it at the most acidic carbon is the blue one. Okay, so we'll use these rules to study qualitatively how acidic things can be all throughout the course and this year of organic chemistry. And this has been section 3.4.